Yeah. Okay. Okay. So I just wanted to discuss the few things which I left as exercises during the previous lecture. So this was so let me just pull up my lecture notes. So recall that this was the thing we were doing at the very end. So I was trying to say that if one wants to study Stirling numbers of the second kind, which is what we call S of n comma k, then this is just the number of ways of partitioning the set 1, 2, 3 till n into k blocks, k disjoint subsets. And so we said this is a slightly harder problem. It's not as easy as the NCK or the other numbers. And specifically, this sort of lends itself to the generating functions method. Okay, so what we did at the end was the following. We derived the generating function for this, for these numbers S and K. So I said, finally, here's what we got. But of course, this was only the generating functions expression. And I sort of left this as the exercise. So I said, try doing partial fractions on it to find out the actual formula for these numbers S and K. So did anyone try partial fractions? Let me copy this. Okay, no problem. Let's do it. It's got, well, you're going to get many terms. So let's write out all the denominators. So this is going to look like something over 1 minus x plus something over 1 minus 2x and so on. So let me just write all of them out in one stroke. If we say this is r going from 1 to k, some coefficient over 1 minus rx. Right? So this is the partial fraction decomposition. And what we need to do is to find out the values of the BRs. So how does one do this? So we said we can just put x equals so maybe that x power k also I will pull out. So that's not so important. So I'm just going to try and write out the partial fraction decomposition for 1 over this product. Okay, so now let's just see. Let's apply the usual partial fractions idea. So we just multiply both numerator and denominator by this entire denominator, and we just see what what the coefficient has to become. So can anyone help me? What should BR look like in general? Or what is given B1? That will already tell us how the other terms are. So what should B1 be? So what should we do after multiplying both sides by the denominator? What value of x will you substitute to find B1?
One plus x square.
Sorry, what?
1 over 1 minus x.
So B1 is like this, right? B1 by 1 minus x. So this is what the partial fractions plus B2 over 1 minus 2x, B3 over 1 minus 3x, and so on. And that is equal to 1 over 1 minus x, 1 minus 2x, till 1 minus kx. So this is what I'm trying to solve. So what should we do? So the usual thing is to multiply both sides by this entire denominator, right? And then figure out what the answer is. But in fact, to quickly get b1 alone, I don't need to multiply by the whole denominator. I can just multiply by 1 minus x on both sides. So let's do that. So it's just 1 minus x, 1 minus x, and so on. And now let's put x equals 1. Okay, so what does that give you? b1 equals 1 over the product of all the other terms in which I have substituted 1 for x. So this is like 1 minus 2, 1 minus 3 till 1 minus k. So this is b1. Okay, so another way of writing it is there is a negative sign. There are how many k minus 1 terms, and there is 1 into 2 into 3 till k. So that's k factorial. So that's what b1 looks like. Okay, but more generally, BR is a similar idea. You multiply both sides of the equation by 1 minus Rx and then put x equals 1 minus R. Okay, so let's do that. So BR is a similar idea. Multiply both sides by 1 minus Rx and put x equals 1 minus R. Will give you the following. So the denominator look like 1 minus Sx. So this is what the denominators look like, 1 minus Sx. Right, and this is for s equals 1 to k. But now I have to multiply both sides by 1 minus Rx. So now that one term vanishes, and now I have to put x equals 1 by R. So this is the final answer. So I've just done all the steps sort of in one go. So that's the value of BR. Okay, and let's simplify it a little bit. So again, notice that just like I did in the previous example, I will put some minus signs separately. So I'll write this as R minus S. So the denominator doesn't have the factor 0 there. And what power of R goes to the top? R power?
K minus 1.
K minus 1, yes. So it's all except one term, absolutely. And now let's again pull out some negative terms. So observe that the denominator is a mixture of positive and negative terms, right? So I want to make it fully positive. I want to pull out the negative signs from the denominator. So how many negative signs are real there in the denominator? How many of these terms are actually negative? So if you actually write them all out, so observe that the first, it starts as r minus 1, r minus 2, and so on. Till r minus r is not there, right? You would have, if you had r minus r, you would have gotten a 0, but that term is not there. So it goes like this: r minus 1 decreasing order till 1, and then what's the next term there? So it keeps decreasing, right? Minus 1, minus 2, like that till it reaches, what's the negative value here? Minus of k minus r. Right? So the denominator is just a decreasing sequence of numbers from r minus 1 to minus of k minus r with 0 deleted from that list. So let's look at what this works out to be. So the positive numbers form r minus 1 factorial. Okay, the negative numbers, they form k minus r factorial, except there's a minus sign also. So I'll put that in the numerator, for example. So what's the minus sign? Minus 1 power k minus r. Okay, so that's my expression. To make it maybe look a little bit more like our NCR, I'll just put one additional factor of r on numerator and denominator. So let's just simplify this to r power k by r factorial on the bottom, k minus r factorial, then minus 1 power k minus r. So that's the value of the constant here. Okay, so we have managed to simplify the constant. So now let's go back and write out what this expression looks like. So, I mean, maybe we won't write it out in full. BR, the value of BR we have worked out. Now this is the final expression. And what did we want? So we wanted to find the formula for S and K. Okay, and S and K is just the coefficient of x power n in this expansion. Okay, so finally, we're almost there. Finally, the coefficient we want which is the Stirling number, is just the coefficient of x power n in the expression x power k multiplied by br by 1 minus rx. R goes from 1 to k, where we explicitly know the BRs. BRs are just, what did we say, minus 1 power k minus r power k by r factorial k minus r factorial. R power k minus 1 power k minus r factorial k. So that's the value. Okay. And so why did we do all this? Why did we do partial fraction? In the earlier examples we looked at in the lecture, the idea was if you did partial fraction, then this can be expanded as the geometric series, right? So we can now find the coefficient of, we can write out the power series in full. So now let's just do the geometric series expansion. So 1 by 1 minus rx is 1 plus rx the whole squared, rx the whole cubed, and so on. So what does that finally give me? It says that this Sn k that I'm looking for is therefore the coefficient of x power n in this whole product. Okay, so let's find out what is the coefficient of x power n in each of those terms. So that product is it's actually a summation, right? So I have to write, let's rewrite the answer. So I want to find coefficient of x power n in the summation r goes from 1 to k, x power k br into, so 1 minus rx, I have to write like this, 1 plus rx plus r squared x squared plus r cubed x cubed, and so on. So this is the final expression from which I want the coefficient of x power n. Now, total coefficient from this entire term, so br is just a constant, it's a number. So let's only focus on the power of x. So how will I get x power n in this product? Which term will contribute? What is the coefficient of x power n?
N minus k.
Okay, wonderful. So only the n minus k term is going to contribute because there's a k in front. So I need to go till I find the term r power n minus k x power n minus k. So that's the only contributing term. Okay, so the net coefficient is the following. For each value of r, I have one such contributing term. So this is now the summation. R goes from 1 to k. Each term br, there's a contribution r to the n minus k from that term. Did you do it right? Yeah. Okay. So we know what br is. So we just now finally have to put the two together. Okay. So final answer therefore becomes S and K is therefore, it's given as a summation. It's R going from that where 1 to k of br into r power n minus k. But this is br. Okay, so I take br, if I multiply it by r to the n minus k, what will happen is this power of r on top, I have to do one further n minus k. They will totally give me an r power n here. Okay, so br into r power n minus k will give me an r power n on top. So this is r power n, and then the bottom is r factorial k minus r factorial. Okay, so you can sort of see why this this expression was, when I said there is no easy way to compute this. So by the way, the summation is only over r here. So okay, yeah, I can't pull anything out. So this the r itself is part of the summation. Okay, so that's really our formula for S and K, if you wish. Okay. So any questions on any of this overall method? So I mean, this is a sort of a great success of the method, if you wish, because it was very difficult to find the number of set partitions into k blocks. But once you put all this, first you got a recurrence relation. Remember, that was a key step. So recall the recurrence relation that we obtained. But this argument was okay. This was easy because it was exactly the same sort of argument which we used for just the NC case, right? So n minus 1, k minus 1 plus the number of partitions in which n occurs together, right? So that is n minus 1 k. So this was the recurrence that we derived. Okay, and this was for some appropriate values of n and k. And like I mentioned, the only difference between these numbers and the usual NC case is that this coefficient is a 1 in that case. Here it is a k. Okay, but the method is absolutely the same. I mean, even there you could go back and try and derive a generating function. Okay, so that's one of the things I want to mention. So there was one other small thing I said at the end that so this came up when we were wondering whether we could have done all this over just the integers versus over the rational numbers, right? These formal power series that we define, did we really need to say? So I had initially said complex number coefficients. That's not required, but it's probably not enough to always only assume integer coefficients, because I said that sometimes it's actually useful to consider a different type of generating function, which I said is called the exponential generating function of the sequence an, which looks like an x power n over n factorial. Okay, so let me just show you a place where that occurs naturally. So I have this formula for S and K, and so this is counting number of ways of dividing this into exactly K blocks. So if K is 3, I want to divide exactly into 3 blocks. But you can also ask how many ways are there of partitioning a set. I don't care into how many blocks. What's the total number of partitions of a set partitions? Just like the total number of combinations from n objects would be 2 power n. Right? You don't care how many objects you pick, but you pick any number, but how many different ways are there? Total number is 2 power n. Similarly, here we can define something called the Bell number. So this Bn here is usually called the Bell number. It only depends on n, not on k. So here's the definition. This is just the total number of set partitions. So this is just S and k. So Bell number is only for n at least 1, you wish. How many ways are there of how many set partitions are there of the set 1 to n? Okay, so what is that? This is just all ways of partitioning the set. So in other words, it's the sum of all the Stirling numbers where k is now allowed to vary if k goes from 1 to n. So this is called the Bell number, and the Bell here, by the way, refers to name of a mathematician. This is E.T. Bell, who sort of popularized these numbers long ago, almost 100 years ago. But Bell is also very famous for a book. I don't know if any of you have sort of had an occasion to see this book by Bell. Sort of his most famous work, maybe. It's not actually a book on mathematics, but a book about mathematicians. So this is actually called the famous book called The Men of Mathematics. Okay, and it includes biographies of the famous mathematicians from the 17 and 1800s and so on. So it has all the various names after whom theorems are named. So you'll find Euler, for example, Lagrange, and I forget, Galois, certainly, Cauchy, Weierstrass, and so on. Okay. So this is a very interesting book. So if you haven't actually seen this before, I would highly encourage you to sort of take a look at this. Okay, anyway, coming back to this, a Bell number is just the total number of set partitions. And of course, we know a formula for S and K. So all you have to do is just sum over all possible K. So let's do that. So one interesting thing, by the way, about this formula is the following, that this formula is actually, maybe we should have tried this formula out for some example. So here's the, oops. So SNK. So the interesting thing with this formula is the following: that if you put k large, see this is for any k, but the point is, I mean, this is actually for all n's and k's. So the interesting thing is if we substitute, I mean, morally we are thinking of k as a number between 1 and n in order to find s and k. But this formula is rather nice. If we substitute any value of k greater than n, then this just automatically becomes 0. I mean, this is how we defined it, if you remember. But what I'm saying is that this formula also gives you the value 0. Okay. I mean, part of the reason is because the definition, I mean, we got the recurrence relation from this definition. But let's just check it for some silly value just to check that actually works out. So if I take n equals 1, for example, and I put k equals 2, okay, so let's just see what happens. So this is now a sum where r goes from 1 to 2. Okay, so there are two values of r here. I have to take r equals 1 and r equals 2. So let's do that. So this is minus 1 power 2 minus 1, 1 power 1. So maybe I'll just call it, okay, 1 power 1 over 1 factorial plus just minus 1 power 2 minus 2, r is 2, n is 1, divided by r factorial is 2 factorial 0 factorial. Okay, so observe this is what it becomes if I put n equals 1 and r equals 2, and this is the first term is minus 1 and the second term is plus 1. Okay, so I get a 0. Okay, so it's sort of an interesting thing. This number is, I mean, this sum here, if I put k bigger than n, the sum is always 0. Okay, so that's an interesting observation. Now let's just use that. So this Bell number Bn that I defined, I said it's the sum. I should take k going from 1 to n of these SNKs. But let me just do sum from 1 to infinity of the SNKs. Because of course, once k is big enough, these SNKs are just 0. Right? So let me just do an infinite sum, because then you'll start seeing some familiar numbers here. So let me sum this. K goes from 1 to infinity. R goes from 1 to k, minus 1 power k minus r power n. And how should we sum this? Any suggestions on what I could do to find this sum? Broadly simplified. So when you have a double sum, one of the standard tricks that we use is to let's try interchanging the two sums. So you know, often that sort of trick works. So here I'm just going to do the k first and then do the summation over r. Okay. So now how does one interchange? So suppose I want to rewrite this as a sum like this. I want outer sum to be sum over r, inner sum to be sum over k. Okay. So then how should I write the limits of the sum? Any suggestions for k, for example? And you've probably seen things like this when you do double integrals and so on, right? I mean, there are regions of integration. So if you sort of look at what the summation varies over, this is over all k and r. So let me maybe write the k-axis and the r-axis. Okay. K varies from 1 to infinity for all integers. These are possible values of k. And for each value of k, the values of r are only between 1 and k. Okay. So which means I'll draw the line y equals x, and if k is 1, then r can be at most 1. If k is 2, r can be at most 2, and so on. So this is really the region for which r is varying. For every fixed value of k, r only goes from 0 to k, or 1 to k maybe. R goes from 1 to k, so not even 0. So I have to sort of shift all the axes a little bit. Let me just draw the axes differently. So the axis, this is really the k axis, and this is the r axis. And these lines which I've drawn here are the r axis. Now this, sorry, delete this r here. So this red line is the value k equals 1, and this vertical red line is the line r equals 1. Okay, so you sort of see the region in which k and r vary here. Now, if I change the order of integration, or the order of the summation in this case, I first want to sum over k, and then sum over r. Right? So I'll fix a value of r, and then I'll see what are the possible values that k can take. So if I do it like that, what will I get? So r can take any value from 1 to infinity. That is possible. But once I fix r, what are the possible values for k?
K equals R to infinity.
K goes from r to infinity. Absolutely. Okay, so is that what I want to do here? I suppose. So k goes inside, k goes from r to infinity, and outer summation is from 1 to infinity. Absolutely. So this is now, let's write the summation again. This is now minus 1 power k minus r. Sorry, I can't remember the terms. R power n, r factorial k minus r. Okay, so that's the value of Bn. And now let's see, does this interchange of summation help us in any way? Is the inner sum any easier now? Can you pull something out of the inner sum?
R power n by r factorial.
Absolutely. So r is really a constant as far as the inner sum is concerned, right? So this is r equals 1 to infinity. R power n by r factorial is not changing when k changes. So as k goes from r to infinity. So now it looks like k minus r by k minus r factorial. Does that look familiar? Some change of variable for the variable of summation will help.
K minus R equal to 0 to infinity.
Wonderful. So let's put k minus r as a new variable. So that will now mean this is summation, call it s maybe. S is just k minus r. So then s goes from 0 to infinity. And this is minus 1 power s by s factorial. So what is that?
Power minus 1.
E power minus 1. Absolutely. Right? So this is just the series for e power x, but with minus 1 in place of the x. So the answer therefore, this is very strange. This is some really mind-blowing formula for the Bell numbers. It says that it is just 1 by e times summation r power n by r factorial. Okay, so it's sort of very strange for the following reason, that the left-hand side really is, see, the left-hand side is finally an integer, right? It's a positive integer. And the right-hand side is sort of some strange thing. It's summation r power n by r factorial. See, this r power n by r factorial is not like, I mean, it is not, it's not an e power x form, right? E power x is like x power n by n factorial. But here, this r is part of both things. It's some strange series which converges to some number. Then you take that answer and divide it by e, and what you get is actually the integer b. Okay, so it's absolutely mind-blowing formula, but it's not very easy to calculate with this because, I mean, as you can see, this is an infinite sum here, r power n by r factorial. So you'll have to convert somewhere. It's not clear what, that by e should be this and so on. So this is not very convenient, but it's very beautiful. I mean, and amazingly, we have obtained all this just by fooling around with generating functions. Okay. Any questions on any of this so far? Okay, so this is valid for n at least one. I guess it's also valid for 0 because if you put n equal to 0, then that's just going to give me 1 by r factorial, which is e itself. Right? So b0 is 1. So it's also okay for 0 because b0 will just then give me e by e, just 1. So that's how, I mean, we defined S00 to be 1. Okay, so so I just had one last comment on this, which is related to this whole business of exponential generating functions. So notice that we started out wanting to count SNKs. Then when we add up all the SNKs, it sort of seems to have some sort of exponential series behavior, right? There's suddenly some E is coming into play. And so in fact, one can take this one further step and look at the following. So consider the series for the bn's also. So let's even take one more generating function. Maybe I won't call the variable x again. Let me call it t. This is now the generating function for the bn's. Okay, bn t power n. So consider this generating function. Now, let's see what we can do with it, since we already have an expression for bn here. So this then becomes summation n goes from 0 to infinity. What is bn? Bn is 1 by e summation r goes from 1 to infinity r power n by n factorial, right? This is bn 1 by e times this. Yeah. Okay, and so then we have to sum this times t power n. So this 1 by e is anyway a constant that we can just pull out. So this is going to be my expression. Sorry, by r factorial. R power n by r factorial, right? Yes. Okay, now it turns out, and I mean, we'll just do this in a minute, that, so this, remember, is what you would call the ordinary generating function of the bn's, of the Bell numbers. But instead, suppose we look at the exponential generating function of the Bell numbers, which, as I told you, is the following generating function. You will just take the series bn p power n by n factorial. Okay, so you form this new generating function. It still has the same information as the bn's. It's another way of encoding the bn's, if you wish. Right? This is one way of encoding. This is another way of encoding. And depending on the context, one or the other we will have a nice compact form. So in this case, it turns out that the exponential generating function can actually be written in a very simple form. So this is my exponential generating function. Now let's play the same trick again. Let's see if we are able to sum this up. Okay. So what is this again? Like I did before, what will I have to do? I must, what should I do? I should maybe interchange the order of the summation. Let's see if that trick works again. So here again, n r, n goes from 0 to infinity. Let me say is the n axis, r axis. In this case, n goes from 0 to infinity. For each value of n, r goes from, oh, this doesn't matter. This is just, they don't depend on each other, right? Okay, wonderful. I don't need to worry. I can just interchange the order without any problem. This is now r goes from 1 to infinity and n goes from 0 to infinity. Okay, so I'll do the inner summation with n rather than r. So what does this become? RT power n by, so I'll pull the r factorial outside, keep the n factorial inside. This is okay. So I'm just applying the same trick that we just did, interchanging the order of the summation. But here it's easier because they're running independent of each other. One goes from 0 to infinity, another fellow goes from 1 to infinity. So what is this summation now? This inner summation. E power RT, absolutely. So observe, it became e power RT because we sort of went and said, oh, wait, let's change this a bit. Let's modify this definition to n factorial. Because I did that, this thing now becomes an e power RT. Okay. So this is now an e power RT. If I had not done it, what would I have gotten at this step? Suppose I had not taken the exponential generating function. Instead, suppose we had worked with the other kind that we talked about, the ordinary generating function. That is, don't put n factorial, just take bn t power n. Then everything till now works, but what would I have gotten here? Instead of this, I would have gotten, instead of e power rt, this is the geometric series, right? I would have gotten 1 by 1 minus r.
1 by 1 minus.
Right? So that's the only difference. Okay. But it turns out e power rt is better for what I'm going to do next. Okay, so let's sum this up. 1 by e summation r goes from 1 to infinity, 1 by r factorial times this. Okay. Now what is this? This should be familiar. What is e power rt by r factorial? Summation r going from 1 to infinity.
E power t.
Okay, wonderful. Excellent. So observe, this is just e power t whole power r, right? E power t whole power r is e power rt. So this is actually again another exponential series where instead of x power r by r factorial, x is like e power t. Okay. So, but almost I'm sort of missing a term, which is see r equal to 0 is not there. Right?
Subtract 1.
So I just have to subtract 1. That's all. So what I have to do really is I can start it from r equal to 0, but then I must subtract 1 from the answer. Only then it's valid. Okay, so let's see what we get. 1 by e. Now this is again an exponential. So this is like e power rt. E power t. Sorry, e power t minus 1. So that is the answer. E power t minus 1 divided by e. Okay. Again, an absolutely mind-blowing formula in some sense, because all we started out is this, we are trying to keep track of the total number of ways of partitioning a set into disjoint subsets. And the total number of ways are these coefficients bn. What we have just proved is that if you encode those coefficients in this following manner in terms of this generating function, this exponential generating function, then the final answer becomes something very, very simple, that it is just e to the t minus 1 by e. Okay. So this, whatever, so observe that this is now some power series again. See, what is this e power t? E power t minus 1 divided by e. This is again some power series in e, right? So I can write this out as a full power series. So this is some power series. In powers of t. And what we are saying is that power series is exactly keeping track of the Bell numbers. That is exactly the coefficients of that power series are going to be the Bell numbers, provided you take this t power n by n factorial as your you put an additional n factorial in each term. So that's really the final crux of this whole matter. Okay, so this is an example again where exponential generating functions give you nice answers, whereas if you had, like I said in this step, if you had just gone with this answer 1 over 1 minus RT, the ordinary generating function, then the next step is a problem. See, what is 1 over 1 minus RT divided by R factorial? This summation doesn't have a nice answer. You can't make that into something nice. Whereas this becomes something very, very beautiful. Okay? So that's somehow the crux of the whole argument. Okay, any questions on any of this so far? Okay, so if not, let me sort of talk about another thing which I promised to say something about in the lecture, which is these, what I call the Q binomial coefficients. So this is again related to well, it's related to generating functions. So let me just tell you the definition of what this is. So this is like binomial coefficients, but it's also some polynomial in Q. Okay, so let me define these for you first. So the definition of the following. See, what is a binomial coefficient? If I just say n choose k. And so let me start using this other notation, the standard notation for n choose k. So n choose k is just the number of ways of choosing k things. Number of ways of choosing k, let's say, numbers from the set of numbers 1, 2, 3 till n. Okay, but suppose you also want to do the following for each choice. So don't just keep track of the total number of ways of choosing, but you keep track of slightly more information at each whenever you make a choice. Okay, which is the following. For each choice, let me say, so if I have a subset, so if S is any subset of 1 to n, let me say sum of S will just denote the sum of all the numbers. It's the addition, summation, what shall I call it? I ranging over S. It's just a sum of all the numbers which belong to S. Okay. So this is, I'm now going to keep track of this additional information. So let me do the following. I will, for each subset, so let's consider the following sum. Okay. So take a subset S of 1 through n of cardinality k. Okay. So the sum ranges over all subsets of cardinality k. And for each such thing, I'm going to do the following. I'm going to put one, let me keep a variable. So the variable is called Q. That's why it's called the Q binomial coefficient. I'm going to say Q raised to the sum of that subset. Okay, so is my definition clear? So let me give this a name. This is Fnk of Q. So what have I done? I've almost done something like this. I've chosen k numbers, but whenever I make a choice, I'm going to sort of count it with the weight q power the sum of the numbers. Okay, so for example, if I take the numbers 1, 2, 3, so what is f3, let's say f3 2 of q will mean I have to choose two numbers out of these three numbers and I should add them. Okay, so how many ways are there of choosing two numbers from these three numbers? I have three choices. I can either choose 1 and 2, 1 and 3, or 2 and 3. Okay, these are the three possible subsets S. And for each subset, I have to keep track of its sum. So the sum here is 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 3 is 5. Okay, so the polynomial that I'm finally writing is this q cube plus q power 4 plus q power 5. Okay, so is my definition clear? So here's my question for you. Here's my very first question. So this is always a polynomial in Q. That is clear, right? For every choice, I've written a monomial. That's all. So it's a polynomial surely. For example, this was the polynomial. But if I substitute Q equals 1, what will I get?
Number of ways of choosing k.
Number of ways of choosing?
Choosing 2 from 3. Number of ways
Correct.
of
That is
choosing 2 numbers.
correct in that example. And if I take fnk in general, this is just nck, right? Because for each way of choosing k things, I get one monomial, q power that. But when I put q equal to 1, that monomial will just become a 1. Okay. So for each choice, I get a contribution of 1. And the total number of choices is exactly nck, number of ways of choosing k numbers. Okay. So that's the first observation. Instead of nck, you have just created sort of for every choice, there is some monomial. That's all. It's become, sort of a thickened version, as it's said sometimes. Each number has been converted into a monomial. That's all. Okay. Now, so that's one. The other thing which you may notice here is that this polynomial doesn't begin with a constant in general. Right? In fact, it will almost always never have a constant term. It will begin with some lowest power of q. Okay. What's the lowest power of q in this? What's the smallest power of q you can expect to get? So in general, so here's my definition. Remember, which choice will give me the lowest power of q?
One plus 2 plus 3. Okay.
Till k, absolutely, right? So I have to choose k numbers.
Okay.
I must choose the k smallest numbers, right? So which choice will give me the smallest power of q? If I choose the k smallest numbers, 1, 2, 3 till k, when I choose them, that's going to be the subset which will give me the smallest power of k, right? So the lowest power of q is exactly 1 plus 2 plus 3 till k. I mean, this you shall make this q to the 1 plus 2 plus 3 till k. That's the smallest thing which I'll get. Of course, we know what that is, k into k plus 1 by 2. Right? So always this polynomial will start only from that power of q. Okay. And so what you can do is you can pull out that power of q. So f and k of q, you can pull out that power of q. Okay. And what's left is called the q binomial coefficient. So this what's left is usually written, this is the notation, it's called n choose k, but I write it with square brackets here, and sometimes we put a q there. Okay, so what is this? This is actually again a polynomial. This is the usual notation, but this is now, remember, this is again a polynomial in q. Okay, so in that example that we just did, so what is 3 choose 2q, for example? Okay, so we did the following. We said f32 of q looks like q cubed plus q power 4 plus q power 5. And from that, I pull out the leading power, I mean the lowest power of q. And what's left is called the q binomial coefficient. So this is exactly your 3 choose 2q. Okay. So again, interesting question. What do you get if you put q equal to 1 into this? So I take the q binomial coefficient and choose kq. And now I substitute q equal to 1. Then what do I expect to get? So remember, this is the definition.
And it's in CK.
You will get the same answer in CK. Why? Because this is just going to give you a 1. That's all. Right? So this is now just the ordinary binomial coefficient in CK. Okay, so that's sort of another reason. I mean, the q binomial coefficient is just like the usual binomial coefficient, but somehow you made it into a polynomial in q. That's it. Okay, so there are many interesting properties. So we probably won't have time to go into all this, but I'm mentioning all this because it's something that you can sort of look up. Wikipedia and many other sources have lots of interesting things about it. But I want to sort of pose the following problem, which is similar to what we have proved about NCK. So remember, let's switch to our usual NCK notation. NCK, we proved this recurrence, right? N minus 1 CK minus 1 plus N minus 1 CK. Okay. Now, I want you to sort of think and tell me what will be the corresponding recurrence for the Q binomial coefficients. If I take this polynomial NCK Q, how does this relate to these two guys? N minus, so I want you to relate these three things, N minus 1, K minus 1, as well as N minus 1, K. But in fact, before we do this, let's go to our usual definition. So remember, we have an auxiliary function called fnk of Q. That's the one which we really understand at the moment, right? The binomial is only defined as you pull out the leading term from that guy, whatever is left is called the binomial coefficient. But I would like you to sort of think about the following. What is the recurrence relation which connects these three functions? Fn minus 1k. Let's just argue from the same, use the same argument which proved this. Try using that and tell me how it will be modified in this sense. So how did we split it into two pieces here? What was our thing? You have to choose k things from n things. What does this term mean and what does that term mean? This is like a number of choosing any subset S from 1 to n whose cardinality is k. Right? K objects from n objects. But what is this? This is the number of ways of choosing S such that S n minus 1 choose k minus 1, right? So what was our argument? We said, let us take those choices where the number n, for example, okay, one particular guy occurs in the set. So this is all those things in which, let us say, n occurs inside your set. And this second term is the number of ways of choosing a set S in which n is not an element. Okay, so we should write it in. So this is the number of ways of choosing S such that n belongs to S. This is the number of sets such that n doesn't belong to S. Okay, so recall that's how we did it. But now let's do the same thing here. Now remember, this is not just the number of ways. This is for each subset S you pick, you must also keep track of its sum. This is q power sum of S, where S ranges over 1 to n of cardinality k. So what happens if in this case, if n belongs to S, then what am I getting? Is my question clear? So in this case, we said you take 1, 2, 3 till n. How do you choose k elements? First choose n. Definitely n is chosen. Having chosen n, you have to choose k minus 1 more elements, which you choose from the first n minus 1 elements. Okay, that was that. Now, in this case, we also have to keep track of the sums. That's the only additional complication. So how will you argue? F and k will be equal to, well, it won't quite be this. There is an additional factor that you'll have to put in front of it.
That q power n is common for every term.
Q power n, okay. The q power n is there in the first term, definitely. So I have to put an additional q power n because n has been chosen, right? So for every subset of the first n minus 1 that I choose, the sum will also include one more element, which is n. So I have to also add its sum to it. So q power n will come out. Thank you. Yes. And for the next guy, n is not chosen. So there I don't need to do anything. There I just have to choose k elements from the first k minus 1 and keep taking their sums. Okay. So here's the interesting thing. As soon as we went from binomial to q binomial, the way it was defined, here's what happens. The recurrence relation becomes slightly more interesting. There's q power n in front. Of course, this is for the auxiliary function f and k. Let's figure out what it is for the n choose case. What should it be for nck? Okay, so we just have to pull out the leading terms from each of them. So let's use the definition. So f and k by definition is q to the k into k plus 1 by 2 into the binomial coefficient. Okay, and so this is q power n. This is q to the k minus 1 into k by 2, n minus 1 k minus 1. This is q to the k into k plus 1 by 2, n minus 1 k. Okay, and so observe I can cancel off the q to the k into k minus 1 almost. This cancels, this cancels. Well, this also cancels here, except what will I be left with? So observe k into k minus 1 by 2 is only the sum of 1, 2, 3 till k minus 1. Whereas what I'm cancelling off is the sum of numbers from 1 to k. Okay, so when I cancel one, I'm left with q to the minus k. That's left. Okay, so let me just do this here. So this is q to the n minus k. And that's the final answer. So after simplifying, here's what we get. Q to the n minus k times this plus this. Okay, so that's the recurrence for these binomial coefficients, and that's like the that's like the Pascal's triangle. So now you can actually write down all the values of the q binomial coefficients by just starting with the same Pascal's triangle idea. Start with 1, 1, 1, 1, and then the next row you can work out from. It's a sum of the previous two, like before, except it is there is sort of a q which you have to throw in every now and then. So this one of the two terms in the previous row will have to be multiplied by q power n minus k. The other term will only have 1. You're not multiplying it with anything. Okay, so I just want to sort of end by pointing out that these q binomial coefficients actually also occur in the sort of thing that Anirban has been talking to you about, which is about finite fields and so on. So here's the other interesting aspect of this. See, what is this nck? So recall suppose I have a finite field. So I take fq power n. Okay, so q is now, let's say, some prime power. So I'm talking about some finite field here. Okay, observe this q now is actually a number. See, the q that I put in the earlier thing was just a variable that I used for my polynomials. Okay, but there is a certain sort of the choice of the alphabet q sort of comes from here. Q is some prime power, so it's a number, and n is of course some natural number. So what is fq to the n? Well, I'm thinking of this as a vector space. So this is a vector space of dimension n over the field fq. Okay, take an n-dimensional vector space and observe that this is a finite set. Okay, the interesting thing is that fq power n is just a finite set with q power n elements. Okay, you can just think of it as all column vectors, and therefore you can ask the following questions: how many k-dimensional subspaces does it have? Okay, so here's a natural question that you can pose: how many k-dimensional subspaces does this n-dimensional space have? Okay, and the interesting answer is that it's exactly the q binomial coefficient. Okay, so we are sort of out of time, but I would sort of encourage you to think about how to prove it. The way to do it is to show that this number that you are trying to find. So maybe you can give this a temporary name, the number of k-dimensional subspaces of fq to the n. So if you call this number, so observe this again a counting problem. So if I call this some d of n comma k, some new number, then show that this has the same recurrence. So now for everything I'm doing here, q is some prime power, q is a number. Okay? So now show that that number d and k satisfies the same recurrence here that you have. Okay, so it is you have to show that d and k is also q to the n minus k d n minus 1 k minus 1 plus d n minus 1 k. Okay, in other words, counting k-dimensional subspaces in n-dimensional space, you have to break it down into counting k-dimensional subspaces in an n-1 dimensional space and counting k-1 dimensional subspaces in an n-1 dimensional space. Okay, and when you think of it in those terms, it's sort of clear what you should do. In the sense, say I have some ambient n-dimensional vector space, you fix some hyperplane. Let's say you fix the x, the one of the hyperplanes. So this is an fq to the n minus 1. Okay. Now you can ask, okay, look at subspaces. Subspaces are of two kinds, which are you want a k-dimensional subspace. Look for k-dimensional subspaces which are fully contained inside this this n minus 1 dimensional space you have fixed. Okay. So I want those which are fully contained and those which are not fully contained. Okay. And you have to show that the number of those which are fully contained will be this number, and the number which are not fully contained will be this other number. Okay, so this is a nice relation. I mean, it's a counting problem, but it's actually a counting problem in finite fields, and it's finally related to this beautiful thing called the Q binomial coefficient, which in turn is sort of really, it's related to our usual binomial coefficients. It's related to generating functions. It's sort of, I mean, it ties together many different ideas together. So this sort of another thing which, if you have a lot of, whenever you have free time, I would sort of encourage you to look up Wikipedia or many other sources. All of them are actually already very good about these Q binomial coefficients, and see what other beautiful properties there are. Okay, so I'll stop what I have to say. If there are any questions and so on, of course, I'm happy to take them.
Participants, feel free to ask any questions. Okay, sir. Thank you, sir.
Sorry, is there a question?
I think there is no question. Participants?
There is some question in the chat.
Okay. Let me look.
Audience reading further on Q binomial coefficient, please suggest some references.
For further reading on Q, for further reading on Q binomial coefficients, there are some references. So, I mean, I would just start with Wikipedia. Actually, I think Wikipedia already has tons of very interesting things about Q binomial coefficients. And if you sort of look at the references they suggest in that Wikipedia article, that might be a good starting point. I don't think our the Rosen and so on doesn't have anything about it. I think I will have to think. Maybe I can look it up and sort of send Guruswamy or somebody, or maybe on the WhatsApp group, I can just send out some references.
Okay, sir.
Yeah, I can't think of anything offhand. Yes, but Wikipedia is a very good place to start.
Okay, sir. Thank you, sir.
Okay, so that's my last session, and so thanks again to Professor Radha and Guruswami for this very nicely organized session, and thanks to all of you for participating.
Thank you, sir.
Thank you.
Thank you, sir. Thank you
Thank you,
for
sir.
your wonderful
Thank
lecture,
you.
sir.
Thank you, sir. So participants, please fill the feedback form and the evaluation form as early as possible. Thank you.
Thank you, sir. Any other thing you want to share to the participants?
Yeah. No, ma'am. No, ma'am.
Okay, sir. Okay. Thank you, sir. We'll see you in the evening.
Okay, ma'am. Thank you.